One heavy-hitting user can bring your entire API to its knees, and you can't just ban them. They might be your biggest customer. Rate limiting solves that, but if you do it wrong, you'll throttle your best users along with the abusers. We saw a real-world case where a platform started getting flooded by a few accounts sending bursts of hundreds of parallel requests. Those bursts ate so much capacity that everyone else's requests timed out. Adding a dynamic rate limiter gave those heavy senders 429 errors, forcing them to slow down while letting the quieter users through. No bans, just fairness. That's the core promise of rate limiting. It's not just about blocking abuse. It's about keeping the service available for the majority of well-behaved users when the noisy ones spike. You see rate limiting everywhere. Stripe enforces per API key limits on mutations to prevent runaway scripts. GitHub caps unauthenticated API access at just 60 requests per hour by IP, and 5,000 per hour once you authenticate. Every major public API, from Google Maps to Twitter, uses some form of it, but the real art is in the algorithm you pick and where you put it. There are 3 fundamental algorithms. Token bucket lets you save up a burst of tokens and spend them quickly, then refills at a steady rate. A leaky bucket enforces a constant outflow rate, queuing excess requests, which smooths traffic but adds latency. Sliding window tracks events in a moving time window for precise counts, but it's more expensive in memory. Token bucket is the most common. You define a rate, say 100 requests per minute, and a burst size, maybe 20 tokens. The bucket starts full. Each request consumes a token. Tokens refill at a constant interval based on the rate. A request arrives. If there's a token, it's processed and the token is removed. If the bucket is empty, you get throttled. The code is straightforward. A token bucket object holds the maximum capacity, the refill rate, the current token count, and a timestamp of the last refill. When consume is called, it refills tokens based on elapsed time, then checks if at least one token is available. If so, it decrements and returns true. Otherwise, false, and you send a 429. Token bucket is simple, but not exact over a strict window. It only guarantees the average rate over time, with permitted bursts. For billing or strict windowed limits, you need sliding windows. The log-based sliding window stores a time-stamped list of every request and evicts old ones. It's precise, but memory-heavy. The counter approach approximates by dividing the window into smaller segments and counting per segment, trading a little accuracy for much lower memory. Where you enforce the limit matters. At the edge, a CDN can reject requests before they even hit your infrastructure. An API gateway can do per route or per consumer limits. Inside the application, you have the most context. You can do per user, per endpoint, and even dynamic limits. But you also waste server resources if you're already under load. The earlier you throttle, the better. When you run multiple instances of your service, you need distributed rate limiting. A common pattern is to store the bucket state in Redis. You use a Lua script to atomically check and decrement tokens, because a naive check then update would have race conditions. 2 parallel requests could both see a token and consume exceeding the limit. For a sliding window in Redis, you can use a sorted set where each member is a unique request ID and the score is the request timestamp. For each new request, you add it to the set, then remove entries older than the window, and count the remaining. This gives exact per-window counts atomically, but high-throughput systems can cause memory pressure because every request adds a member. Distributed rate limiting introduces its own headaches. Redis failure or network partitions can leave your limiter either too lenient or too strict. Clock skew between application nodes can shift window boundaries and cause unfair throttling. And when you have millions of distinct rate limit keys, like one per user, Redis memory can explode. You need to choose data structures carefully and set TTLs aggressively. When you do throttle, always return a proper HTTP 429 status code, along with a retry-after header indicating how many seconds to wait. This lets well-behaved clients back off automatically. Without that header, they might retry immediately and waste even more resources. Burst handling is where many rate limiters fall down. A token bucket with a large burst can pass a spike of traffic that overwhelms your database, so you must set the burst size to keep your downstream safe. A rule of thumb: burst should never exceed the capacity your database or backend can absorb within a few seconds without latency degradation. For a service that handles 100 requests comfortably, A burst of 20 is often safe. A burst of 200 could be deadly. So which algorithm when? Use token bucket for most API protection. It's simple, fast, and naturally allows bursts. Use a sliding window counter when you need accurate per minute or per hour billing. Avoid the exact sliding window log unless you absolutely require perfect precision and can afford the memory overhead. And always prefer edge enforcement unless you need application-level context for per-user dynamic rules. A critical design choice is per-key fairness. If you set a global limit of 1000 req US, one noisy user can starve all others, so you almost always want per user, per API key, or per IP limits. This ensures that even under attack, each client gets its fair share, and no single user can block the rest. Let's revisit that scenario. A typical platform might see normal users making around 5 requests per second each, with P99 in latency around 150 milliseconds. Then, a bulk automation user fires off 200 parallel requests per second, saturating connection pools and causing the database to spike to 95% CPU. Latency for everyone jumps to 5 seconds. By introducing a per-user token bucket with 10 requests per second and a burst of 5, the heavy user immediately gets 429s on excess requests. Their automation adapts, their effective throughput drops to the limit, and the rest of the user base sees latency return to normal, often within seconds. For an even smarter system, you can make the limits dynamic. If a user consistently triggers 429s, you might temporarily lower their rate limit to further protect the system, then restore it once their behavior normalizes. This adds a feedback loop that tames aggressive clients without manual intervention. So here's what to remember. Rate limiting is not about blocking users, it's about preserving service for the well-behaved ones when the noisy ones spike. Token bucket is your go-to algorithm. Set burst sizes to protect your downstream, never just to look generous. Always include the retry-after header. Enforce per user or per key limits for fairness. And if you distribute your limiter, mind the race conditions and memory cost. That's rate limiting, a simple idea that, when done right, keeps your platform alive under load without punishing your good users. Thanks for watching. I hope this one was useful. See you in the next video.